Data augmentation. TensorFlow makes it very easy to implement data augmentation. In implementing data augmentation, we just define a sequential model, and then in this sequential model we have a list of data augmentation strategies we are going to employ. Now the first one we're using is this pre-processing the random flip. If you get to the documentation under TensorFlow here, tf.keras layers, that's we under tf.keras layers, and then in the layers we go to experimental. Under experimental we go to the pre-processing. In this pre-processing now we have the random zoom, rescaling, which we've seen already, random width, text vectorization, which we shall see under text data processing, random width, random translation, random rotation, random height, random flip, random crop, random contrast, and other TensorFlow layers which could be used in processing data. Then apart from this, we have under, because here let's take this back, let's take this out. Under this, here we have TensorFlow or tf.keras. We also have under the tf.keras, that is here we've looked at the experimental, or rather we looked at the layers, and under layers we had experimental. But now if we go directly into the pre-processing, we shall see other functions which could be used. Now note that here these are looked upon as functions, so we have this random zoom function, random shift function, random share, and all that. Same as we have the load image to array to image, which we've seen already. But the difference is that with the pre-processing we had seen previously, that is under these layers right here, these are actually defined as TensorFlow layers. So just like the GRU, let's look at this, just like a dense layer, for example, just like a convolutional layer, these two are defined in that way. Now we shall also see shortly why it's better to work with these transformations as layers. So as we've seen previously, we actually take the pre-processing, we import it from the TensorFlow.keras, the layers.experimental, which we've just seen in the documentation. So coming back to this, we have the random flip. We specify horizontal and vertical. Now for any modifications on this pre-processing units or pre-processing layers, you could always check out on the documentation. Now let's run this, and then we're going to plot out what happens when we do this random flip. We see clearly from here that this image has now been flipped. We also add some other pre-processing layers. We have this, take this off. So for now we have the random rotation. We also have the saturation, which we shall define shortly. For now we consider this random rotation, we run it, and there we go. Then apart from the TensorFlow.keras, the pre-processing layers, we also have the TensorFlow.image pre-processing methods, like this one where we could adjust the saturation using this method. Apart from the adjust saturation, we have adjust JPEG quality, adjust hue, adjust gamma, adjust contrast, adjust brightness, the crop and resize, flip left right, flip up down, and a host of others. So the important point to note here is that these are seen as just methods, whereas those in the pre-processing units are seen as layers. Nonetheless, we could define this in a TensorFlow layer. So this adjust saturation method is defined in the call function of the saturation layer, which we've just created. And as you could see now, we could call it as we had seen right here. So here we're basically calling this layer, which is just like a pre-processing layer, or similar to a pre-processing layer, in the sense that we just stack up these layers in this sequential model. Let's test out another method in the tf.image package. Let's say flip left right. It doesn't need a factor, so we'll take this off. We could, yeah, for now let's leave that. So let's suppose it's saturation. Anyway, we could change the name to flip, so we could call it flip. It's a flip layer, takes no parameter. Now we need to define this right here, define that flip. So there we go, takes no parameter. Run that, get back to this, run again, and that's it. So we'll see how we'll flip this left, right. And this shows you how you could use the methods in the tf.image package, methods in the tf.keras.preprocessing, and then the methods in the tf.keras.experimental.preprocessing. All this could be used in doing data augmentation. But now note that there are some transformations which aren't available in the TensorFlow packages, and these transformations you have to actually write them by yourself. Now let's go ahead and define a custom transformation which we shall call contrast. Now what the contrast does is it takes in the input, and for each and every pixel we multiply it with a constant alpha, and then this result is added with another constant beta. So for our contrast method, alpha and beta are like our parameters, where if we have this contrast function, it takes in this. So we basically have x times alpha plus beta. Now, once we've defined this contrast, we could now have this contrast layer, just the same way we did with a flip. But the difference now is that we're not using a TensorFlow transformation, but we're defining this from scratch. So we're using this contrast, we're taking the alpha, the beta, we run this, taking alpha, beta, and then we call the contrast method right here, which also takes in this alpha and beta. So we'll run that, and then we go ahead with the contrast. So here we have contrast, which takes in alpha, say 2, and beta, say 0.5. Let's comment this so we could see exactly what goes on. So there we go. Now we have our contrast, which we've just defined. If we modify again, we can have, say, 0.1. That's too small, so let's take 0.9. Okay, now notice how the image gets less bright. Could take 0.5. There we go. So what does this mean? It means that if we have images in daytime, we could use this to teach our model how to correctly classify the same images even in the dark. So data augmentation is a very important technique, but depending on your problem, you have to choose the right data augmentation strategy. And also it's very important, depending on your problem, to evaluate the effect of data augmentation on your model's performance, so that you don't go using data augmentations which are not useful for your particular problem. Now that said, we could uncomment this, uncomment that, run again, and there we go. We see that it has been randomly flipped, randomly rotated, flip again, and then a contrast has been added. Could take this to, say, 2, and that's it. So basically, after defining this data augmentation layer right here, all we need to do is to include in our training pipeline. Now there are generally two ways to do this. We could create a new train data set, which we'll call train data set augmented, which takes in the initial train data set, and then for every value or every data point, obviously it contains x and y. So for every data point, it's going to take, for example, because we're doing the augmentation only on x, so it takes the x and then it does the data augmentation based on x. That's basically calling this layer right here. We call this layer, and then the y remains intact. So for every image, we're gonna have this data augmentation or this pre-processing, such that we have the image itself now and its pre-processed version, but the two have the same output, so our data set now has been multiplied by 2. We could run this, and then we have our train data set augmented. See, it specifies that it's a map data set because we've called on this map method right here. Now the second and very efficient way of doing this is by simply including this layer right here as part of the model. We had seen this already with rescaling, but now let's see it with the data augmentation itself. Get into the model. After doing the rescaling, all we just have to do here is call the data augmentation, and then we're taking as input X, and that's all. So either you just include this in your model, since this data augmentation has been defined as a layer, or you transform the trained data set by the map function, which comes with the TensorFlow data sets.